Hey, what's up, students?
Hey guys, Ms. Awad and Mr. Bin here with you talking about Bowens Reaction Series.
You guys ready to rock? Here we go.
So in this video you're going to see not much of our faces again, you're going to see a lot more of our hands, and we're going to cover Bowens Reaction Series for you. So, ready to go?
Alright, if you look in your textbook on page 123, you're going to see a very important chart. If you understand the components of this chart, you'll understand basically the majority of what we're going to learn in this chapter, how the rocks all go together. So if you have to learn one thing, learn Bowens.
And we set up a pretty good start with Bowens Reaction Series in the last video when we talked about the different silicate structures.
I agree.
So we were thinking about being in a magma chamber with a lot of magma that was changing temperature. So it was starting to cool down. And we had, at the beginning, the silicon-oxygen tetrahedra forming, and then bonding with some magnesium and some iron, and forming our first set of minerals, which are the mafic minerals, and then the temperature continuing to cool down. So what I think we're going to think about here is what really happens as the temperature decreases within a magma, if nothing else is changing.
So initially, when it's super hot, above the 1,200 degrees Celsius, things would be going so fast, they would just kind of bump around, nothing would really form, nothing would stick. When temperatures cool down, now you're getting different elements being able to stick together and maybe form the first basic structure. Okay.
So that first basic structure, as we learned last time, is going to be magnesium and iron, or just magnesium or just iron, bonded with the simple silicon-oxygen tetrahedron. And that's what forms our first mineral, which we said was the mineral olivine. And it's easy to remember olivine. It's green, like a green olive.
I would say olivine is olive green.
Yep, you got it. Okay, so as that magma continues to cool down, then what happens, Mr. Ben?
Well, then this guy could actually maybe tumble around and then merge with another guy. It's kind of like when it's cool, or when it's so hot, these would hit and bounce off other tetrahedrons, and then you'd just get this mineral. But when it's cool enough, two of them would come together, and like you were showing, they're going to be sharing, and they can stick together, and then they kind of, silicon fell out, they would kind of tumble around together, making that next structure you were talking about, that single chain.
Okay.
So you're now at the next rock, you're at you're at the next rock, you're at the single chain, you're at your,
Augite, yeah, or pyroxene, right?
pyroxene.
Because augite is one of the pyroxene minerals.
Exactly.
So the pyroxenes are a group, but the most common one that we find in igneous rocks is the augite. So we'll call it pyroxene. I think that's more common in the terminology, so I think that's what students will be seeing.
Okay.
Okay.
So now after the magma chamber cools a little bit, and this single chain basically is kind of zipping around and such, then it could form that double chain you said, where two of them get stuck together. They're more efficient. You're also losing, you said, a lot of those oxygens, so they need to be more efficient. They need to be able to change the ratio of oxygens to silicon, so you get that double chain. Now you're looking at your amphibole. So the longer double chain, so it'd be like another chain of these kind of stuck together going through the melt.
Right. So here's what we have. We've got the single tetrahedra, that's like the olivine, the long single chains, and again, when we say long, these could be millions of atoms in length, or millions of tetrahedra in length. And then we've got our long double chains of the amphiboles, and most of what we're going to see in the amphiboles are going to be hornblende. Now, at the same time that these minerals are forming, using up the iron and the magnesium in the melt, we also have this feldspar that's forming, right? So what about that feldspar?
This feldspar you said has calcium. Now these guys so far don't use calcium in their structure. So this would be a perfect environment for the feldspars to form, because there's really no competition for calcium. So at the same time these guys are forming, olivine, you're now getting this mineral in the chain. We're looking at the chain. he's over here. They call them the discontinuous and the continuous chain in Bowen's chain of reaction. This is the discontinuous chain because when this one is forming, it switches to the next one, switches to the next mineral. This one's called the continuous chain because you continually make feldspars. So in the beginning, nobody's really using calcium. It isn't until you get down here that something else, the amphiboles, are starting to use the calciums. So you got your calcium-rich feldspars forming, and then when they eventually get down to this point where there's some competition for the calcium, then you're getting them made with more of the sodium, till in the very end, when you get way down here, after your amphiboles and your biotites are being made, your plagioclase feldspar is going to be probably mostly made out of sodium. Just sound right?
Okay, so I just want to make sure I understand this. With the feldspars, which are the continuous series, the calcium-rich forms at the high temperature. The sodium-rich or sodium-pure feldspar forms at the low temperature. And in between those two, halfway, there's going to be a feldspar that is 50% calcium, 50% sodium. And a little bit closer to the calcium feldspar, there's going to be a feldspar that's more calcium than sodium. The closer we get to the sodium feldspar, the more sodium there is. So you have a gradation that changes from all calcium to all sodium. But in the discontinuous side, between olivine, pyroxene, and amphibole, the structures are completely different, and the minerals are completely different.
Right.
They don't blend or grade from one to another.
So this one in the structure, you can actually either have calcium or sodium. They're a very similar size molecule that can kind of fit in and fill the space.
Perfect.
Where over here, they're a completely different metals would be joining to your chain.
Good. All right, so once we get down to this point, now it's pretty cool in that magma chamber, right?
Exactly.
And we have our last three minerals that are going to form. So we haven't had any of the potassium come out of the melt really yet. And an appreciable amount of the potassium is going to go into the potassium-rich feldspar.
And aluminum would be left because it's light, right? So now you're getting the metal aluminum that's still available in the melt forming in the minerals.
Okay, and then more into the muscovite, or the light color mica.
And you said before that the dark mafic minerals are already used up, so that must mean the muscovite uses minerals that maybe don't have the iron and magnesium so
Right.
much.
It's using those elements. And then finally, when the aluminum, the calcium, the sodium, the magnesium, and the iron are all used up in that melt, what might be left, or what is left, is silicon and oxygen. And then we end up with our quartz, which is the pure silicon dioxide.
Okay.
Right? So the coolest temperature there.
So basically, these minerals are going to be using silica in them and oxygen. In the beginning, you're going to have the highest ratio of your oxygen and silicon together. And as you go this way, you wind up with your putting in different metals and then using them up as you go along until all that's left is just silicon and oxygen. That must mean that there's a lot of silicon and oxygen in the Earth's crust.
There is. And in the mantle, too. Okay, so should we draw out Bowens Reaction Series here? Just to make
like a
sure
bigger
we're good
version
with
of
this?
this? Okay,
Yeah,
we
let's
got
do
this
that.
kind of right here.
Yeah, so let's move these guys out of here, and we can keep these over here. That'll work, right?
Okay, yeah, so we've got our olivine over here showing the simple, the simple tetrahedron.
Right.
And this would be the hottest temperature, right?
Oh yeah, we could put temperature up here. So here's low temperature. And here we have the olivine, then the pyroxene, then we've got the double chain, the amphibole, and then we start to form the micas, so biotite. Easy way to remember that is the black one is B for black, right?
Exactly.
And then, what's that guy?
This guy is the potassium-rich feldspar.
Okay. Can I just write K-spar? Okay. And then we do muscovite. Do you know how muscovite was named, Mr. Ben?
You got me on that one.
Okay. I think muscovite was named for the Muscovite region in Russia. I don't know where I came up with that.
That must have been where they discovered it or found large quantities of it and first really researched it.
And then we've got quartz at the bottom.
Okay. So way up here would be above the 1200 degrees Celsius. And so everything's moving so fast it's molten. So there would be no minerals here, right? Because everything's moving so fast, no minerals are forming whatsoever. Now when the temperature drops down to here, then at this point, you're forming the first most basic mineral, the easiest one to form, the single chains. They could bump into each other, but they can't stick because they're going too fast. And you're forming the beginning of the continuous chain of the plagioclase feldspar. Now, these classified as ultramafics, right? Because they're really, really a lot of iron and magnesium.
Yep.
So, now, mafic, the word mafic, that's what? Iron and magnesium, right?
Mm-hmm.
So the Ma is for the magnesium, and the Fic is for iron.
Yep.
So that's these guys right here. And these mafic ones are going to be basically, draw the line about right here. So now these are mafic, and these are forming mostly with the magnesium and the irons, you said, sticking to those, the edge of the oxygens, because you said each one of these wants an electron, right? And so metals give electrons, and so they are attracted to the silicon-oxygen tetrahedrons. And then when you get to this point, now we have the intermediates, and those are a mixture of some of the dark and the light as well.
Yes, I think we're going to want to start and look in our intermediate rocks. We'll start looking for some amphibole and some biotite. We might still have some amphibole in the mafic rocks, but these tend to be a little bit more of indicators for an intermediate composition.
So our let's see if we can move. Because the end of this arrow, put this guy down a little bit.
There we go. That's good. Okay. And then below that, what do we have?
Okay, and now we're down to felsic. So these guys down here, the FeL stands for feldspar. And the SiC is for the silica, like the silicon dioxide, the quartz.
Okay. So now I got a question.
Okay.
We've been talking a lot about, we start with the magma, and we're starting to cool the magma down, and what's happening as the magma gets cooled down.
Right.
But we have to remember that sometimes things go the other way, or we wouldn't have any magma. So, does Bowens Reaction Series work the other way too? If we start out with a solid rock, and we start to increase the temperature, so maybe we're in a subduction zone, where that downgoing oceanic crust is being pushed into the upper mantle, and the temperature is increasing. Could we say that quartz is going to be the first thing to melt?
Yeah, that would probably, like andesite is like light and dark. So could the light stuff that came off the continent that went down with the plate, could that start melting right away and then start rising kind of up? Would that be what's happening? You melt the stuff that's last to form would also be the first to melt. So you would end up, the lower temperature minerals would start melting and become less dense and rise up through the crust. And then you would wind up with that slab of oceanic material, which would end up looking kind of like this before it finally became molten down deep in the earth.
So what I'm wondering is, and I think we're going to get to this in class in another week or so, is if we take this solid crust and we melt it, or we take the upper mantle and we melt it, but we don't melt it completely. We only take it up to maybe 900 degrees.
Okay.
Will we only see this small group of minerals, and the more mafic or ultramafic minerals will remain solid?
So you'd partially melt it.
That's what I was looking for, was partial melting.
So you melt out the light temperature minerals and you wind up with, this area would still be enriched in the darker mafic, and you would basically be, it's kind of like what you were talking about before. You would be then, the lighter temperature minerals would be leaving, or the lighter temperature and kind of lighter in color minerals too.
Yep. All right, that's a lot to think about. I think we're going to think about that and think about how pressure has an impact on this whole melting and crystallization too, as we think more about magma evolving. And then maybe even get into the idea that magmas can also change by other magmas or other rocks getting added to them down the road.
Right, chemically active fluids getting involved in
we'll
the,
come back to that again. Huh?
This is kind of, it is.
All right. Okay, well, I hope you guys understand this segment. We're really glad that you joined us, and good review again. Some more new things to think about.
And again, page 123. If you know Bowens, you know igneous rocks.
Bye. See ya.